Hi, my name is Matt, and I'm going to show you how to set up this painterly post-processing effect called the Kuwahara filter in Unreal Engine 4. I'm using a custom node and a post-processing material to achieve this effect. I'm currently showing off some of the different settings we'll be exposing so you can tweak this effect to your liking. So, what is a Kuwahara filter? According to Wikipedia, the Kuwahara filter is a non-linear smoothing filter used in image processing for adaptive noise reduction. We are going to calculate the average and the standard deviation for 4 regions centered around our pixel. We then use the average color of the region with the lowest standard deviation as our output color. The image here illustrates, the paint brush stroke like effect that this filter creates, which is what we're trying to replicate. So to get started in Unreal, I've downloaded the Sun Temple from the Unreal Marketplace. I've created a folder in here called the Kuwahara tutorial. You don't have to do that. You can throw it in whatever folder structure you want, obviously. I'm just going to find the post-process volumes, and I'm just going to delete the other 3 because I don't need them, because I can illustrate what I'm trying to do with a single one, but you can set this up for as many post-process volumes as you want. Under the post-process material settings, you can find under the post-process volume settings, you can find the post-process materials where you can add one. I'm going to set that to an asset reference, and I'm now going to create that asset. We're going to create a material called the Kuwahara post-process material base. And I'm going to create a material instance of that, which is called the material instance. Within this material, I'm going to set this to be a post-processing material, apply that, and I'm going to drag the material instance into the slot. Your screen will go black. That is intended, as we've not done anything in the post-process material yet. We can resolve that easily by adding a scene texture and setting that to the post-process input and applying that. This should result in a scene that is identical to what you had before. We know we want to implement this filter through a custom node because we're going to need some loops. So I'm going to create this custom node. I'm going to call this Kuwahara, and I'm going to add some inputs to it. There's 4 inputs we'll need. One is the scene texture. We'll need the UVs. We need the radius of the filter, and we'll need the view size or the texel size. So this will be the scene texture. The radius and the texel size. Oh, sorry, the view size. Right now, if I just plug this in, this will do nothing because it's both missing inputs and it's not currently doing anything yet. We're going to write the code for this in an external program, in this case, Visual Studio Code. So you can use other text editors for this as well, of course. Actually, before we do that, I'm just going to hook up color texture coordinates, a scalar for the radius. I'm just going to set that to 5, and the view size. And then, well, as you can see, the output of this is always 1 at the moment. So if you leave that on 1, it will be pure white. Instead, I'm just going to set this up with a scene texture lookup using the UVs. I'm using the scene texture 14. I'll show you where I got that what I got that from. So I'm just going to return that. And as you can see, this messes around with your UVs a bit. And I'm going to show you how to fix that. The reason it's currently messing with my UVs is because I've rescaled this window. There's something in Unreal that doesn't like that very much when you're doing the post-processing. There's a fairly simple way around this. I don't believe you'd get this if you make a build of your game. I believe it should work fine. But if you also want it to work in editor, there's something fairly simple you can do to get around it. You need to make a custom node. Just going to call this screenUV. I filled that in the wrong place. Sorry. You need to remove this input. Call this sceneUV actually. Make sure that this sets to float 2, and then return get scene texture UV parameters. This returns UVs that are better suited for sampling the scene textures through a custom node, and it will keep on working even if you rescale this window. All right, so right now we're again back to where we were already with the post-process input previously, but now what we can do is use this custom node to change the way we sample this texture. We can sample it within a for loop to get those averages, and well, that's what we're going to do in Visual Studio Code now. But before I do that, I was just going to show why this is 14. If you click the scene texture node, there's quite a few options. This is just the 14th element in that list. The reason why I plug it in while I'm not calling it by name is because if you don't have this node plugged in somewhere, you cannot access the 14th scene texture. If you set this to any other option, you cannot access the 14th scene texture either, and that's the one we want to sample. I like just plugging it in. I'm not actually using the scene texture name anywhere to sample it. You just need to have it hooked up somewhere, otherwise it gets compiled out. In Visual Studio, just gonna open a new file. What we're going to do is we're going to start with declaring a few variables that we'll need. So one of them is an array of 4 float 3s in which we will store our averages. Another one is a float 3, an array of 4 float 3s that will contain all our standard deviations. We need a few offsets to use for the sampling, and those are going to use those radiuses that we set up. You could, in theory, do this with a different size for the x and the y. So you get instead of sampling the same amount on the x-axis and on the y-axis, you could sample a different amount on the x and the y-axis to get other interesting effects. How the sampling is going to work is we're going to only use the negative radius and 0, and then we're just going to loop through and add back onto it until well, we all the negative radiuses are going to sample between negative radius and 0, and all the zeros are going to sample between 0 and radius. So we're going to need a float2 for the position of the current sample, and we're going to need a float3 to store our current color. So Now we're going to have to loop through for our samples. So we're going to sample once for every region at first. So just sampling 4 times, 1 time for every region. And for every region, we're going to want to sample multiple times. Well, multiple times on the x-axis and multiple times on the y-axis. So we're going to nest 2 for loops. So j is smaller or equal to radius and j++. And then we do this again, but for k. Our current sample position will be a float 2, that is, so the XID and the YID plus the offset we defined here. So the UV position will now be the UV we're passing in plus that position divided by view size. The UVs are 0 to 1 for your entire screen, so 0 being the left side and 1 being the right side. Your view size is going to be the actual resolution of your viewport. So if you're you need to divide that position by the view size to bring it back into this 0 to 1 range. The color of this specific sample will now be that scene texture lookup that we did earlier, but this time using the UV position, the new one we found, still using texture 14. False. So to calculate the average of multiple samples, for now, all we're going to do is we're going to add the color to it. And for the standard deviation, we're going to add the square of the color to it. It's useful for us to know how many samples we've taken in total. Just going to call that n. And the number of samples we've taken per region is going to be the power of 2 of the radius plus 1. The plus 1 is because this is inclusive. So what we can do for now is we can return the mean 0 divided by n. We're obviously not going to be using this, but this will show you the average color of the bottom left the bottom left region. If I just paste that in, this is going to compile for a little bit. Shader compilation sadly is a little slow when you're using custom nodes, but it shouldn't necessarily affect runtime performance. You do have to be slightly more careful with custom nodes, as the compiler optimization for them is less good than for any shaders you build through the node graph. I just let this compile, and as you can see, you now have a much blurrier output image where every color is the average of a region. So to continue this, what we want to do is we want to calculate these the standard deviation for each one of these regions, and we want to use whichever region has the lowest standard deviation. So what we can do is we need a variable to compare against. In this case, I'll set this min variable to 1. We're going to compare the standard deviation of every one of these regions against this number. If it's lower, we're going to set the min to that standard deviation and the output color to that color. If it's not lower, we're just going to ignore that region until we've been through all of them. So we're just going to cycle through all 4 regions again. And we're going to take the mean and divide it by, we divided by n, so we get the, well, the results you were seeing in Unreal. For the sigma, we're going to do something similar. So we're going to take the sigma, we're going to divide it by n, but we still need to find the standard deviation from this. So what we're going to do is make this value absolute, and we're going to subtract the square of the mean from it. Ideally, we'd want this standard deviation to be stored in a single float value instead of a float 3 or a vector 3. So I'm just going to add a variable for that, calling it sigma f because it's a float. So sigma f equals sigma I dot. I'm just going to add together these 3 separate channels. So yeah, sigma I dot r plus sigma I dot g plus sigma I dot b will it will find the deviation of every one of these channels and add them together. Because this value is absolute, none of them should be negative. Yeah, that means that we just store the difference. We then compare if the sigma f is smaller than that min value that we calculated here, or well, that we declared there. If that is the case, then the min value is now sigma f, and the color value, we can just reuse this color, I think. That will be equal to that mean. All right, and then we return that color. So if I copy this into Unreal, I will just let this compile. So with the round node in, yeah, the steps look a bit better. So one thing I was showing off in the beginning of this video was the ability to only have this affect part of your screen, which is fairly simple to do. The sceneUVs, as we looked at earlier, are, well, it's black on the left side of your screen and fully red on the right side of your screen, which is something we can use for that. So what we'll do is we'll use a linear interpolate on the red component mask of the sceneUVs. So what we want to do is, if this value is higher, we want it to show, so on the right side of the screen, we want to show the Kuwahara filter. On the left side of the screen, we want to show the original, but we still want to add a value. We still want to add a value to that. You might also have to add a component mask here, because there's also an alpha value that's stored. Right now, what it will do is on the left side of your screen, it will not have any of the Kuwahara filter. On the right side of the screen, it will be the full filter, but in between it will be a linear interpolation, and we don't want that. We want it to be a step. So you could use a value step for this. What I tend to prefer to do is use a scalar uh, which I call just gonna call screen fract, because I know these values are going to be between 0 and 1. What I'm going to do is I'm going to add this value to it, and then I'm going to floor it. So this means if you're not adding anything, the value will be 0 for the entire screen. And the more you add, it will be, well, if it's 0.5, the left side of your screen will be 0. The right side of your screen will be 1, which means that you get this step. So just going to let this compile as well. So after letting this compile, if you look at the material instance, and you move the slider, you can see the filter getting activated on the right side of the screen. Currently, you could push this far outside of the range we want, so we can clamp this number. But yeah, that is the effect. I hope you found this video useful. If I missed anything or should explain anything more clearly, please let me know in either the comments or send me a message. And yeah, I hope you enjoyed the video.